Hi class, we continue our study in chapter 13 by moving into section 13.2, and this is talking about the derivatives and integral of vector functions. So this is just basically applying calculus to this concept of vector functions, and it works exactly the way you would think it would. Okay, so let's first talk about derivatives. So the following theorem gives us a convenient method for computing the derivative of a vector value function r. All you have to do literally is just differentiate each component of r separately. No special rules, just differentiate them. So if r is a vector value function of the parameter t, these are the components f of t, g of t, and h of t. R prime of t, just take the derivative of the first component, derivative of the second component, derivative of the third component. That's it. This formula also works in 2 dimensions. Here I just have a 3-dimensional vector value function for you. Okay, one other concept I want to quickly touch on with this concept of derivative is the idea of a unit tangent vector. So a tangent line to C, okay, at P is defined as the line through P parallel to the tangent vector r prime of T. So we also have on occasion to consider this concept of this unit tangent vector, which we're going to denote as the vector valued function t of t here, capital T, and it's just equal to the derivative of the vector value function r divided by the magnitude of the derivative. Okay, so let's just do an example of this. Okay, so let's find the derivative of this vector valued function here. Okay, r of t is equal to 1 plus t cubed I plus te minus tj plus sine of 2tk. Okay, that first I want to find that, and then I want to find the unit tangent vector at the point where t is equal to 0. All right, so the first thing we have to do is we have to differentiate this vector valued function here. So we're just going to differentiate each component. So the derivative of this is obviously just 3t squared. Okay, so that's what, and then the I. Here, t, t to the minus t, you're going to have to use the product rule here. So this ends up just differentiating as 1 minus t times e to the minus t. Both terms will obviously have an e to the minus t. We're just factoring it out, times j. And then the derivative of sine is cosine, so you're just going to need to use the chain rule here. So this just becomes 2 cosine of 2tk. All right, so the next thing we want to do is we want to find the unit tangent vector when t is equal to 0. Okay, so the first thing you need to do is, like, what point does that occur at? Here you're going to see it's the point 1, 0, 0. You would take 0 and you'd like plug it into this, right? So this would be 1 plus 0. This is 0 times 1, so that goes away, and sine of 0 is 0. So it is just the point 1, 0, 0. Okay, so the unit tangent vector, okay, at the point where t is equal to 0, I'm just going to take the derivative of r that we just found here, okay, and plug 0 in and divide it by the magnitude. Okay, so when you end up doing that on your own, you'll end up seeing that it's just j plus 2k divided by the square root of 1 plus 4. So the unit tangent vector here, notice how there's no I. That just means it's 0i. So 0i plus 1 over the square root of 5j plus 2 over the square root of 5k. Okay, you can go on and talk about higher order derivatives here. So just as for real valued function, the second derivative of vector function r is the derivative of the first derivative. Okay, so for instance, if I ask you to find the second derivative of this function here, 2 cosine of t sine of t, the first derivative of this is negative 2 sine of t, and then you take the derivative of that, you end up just getting negative 2 cosine of t. Here you just take the derivative twice, right? The derivative of sine is cosine, and then the derivative of cosine gets you back to minus t minus sine of t. And then the second derivative of this t is just 1 and then 0. So that's how you do that. All right, so one quick slide about the differentiation rules. It's all the same differentiation rules that you would have for regular derivatives. Okay, it's the same exact applied to vector valued functions. So I won't go through all of them, but they are here for you. All right, let's just end talking about integrals. It's also very straightforward. So if you have the integral from a to b of the vector value function r of t with respect to t, right here, Again, all you're going to have to do is just integrate its individual components. That's it. Okay? So just how you find the derivative, you took the derivative of the individual components. If I'm asking you to integrate, you just find the integral of the individual components. So here, if I have the vector value function r of t is equal to 2 cosine of ti plus sine of tj plus 2tk, right? And then I ask you to find the integral of r of t dt. Just integrate these components. Okay, you see that this very easily integrates into 2 sine of t. This integrates to minus cosine of t, and 2t obviously integrates to t squared. Okay, if I put bounds of integration on it, you would treat it just as you would a real valued function. Just don't forget the components I, j, and k. That's important. All right, class. I hope this quick video helped.